Okay, so here's a quick demo to sort of reinforce what Darshak sir talked about in the last lecture. So what I'm going to do is I've got a very simple program here. Okay, so there's an int main. I initialize the port F pins which are connected to LED. There's one variable which I don't really use, and then basically I cycle through the LED values. So this is just the initial, I think, from the first lab that we are using. I'm not going to change it much, but just for you to see. There we go. So this is basically the main program that lands up here in this GPIO port F init, and then of course we go and set everything for port F, and then there's some delay, and so all sorts of things happening here. But that's really not the focus of what we want to look at. What we want to look at is what happens before we land up in main. Okay, so to do that, there's a nifty little thing here called system reset. So let me just do a system reset here. Okay, and the moment I do a system reset, what we can see is that the program counter has gone to 308. So why did it go to 308? Why didn't it go to 0? Okay, so to answer that question, let me put my memory browser here to look at memory location 0, and what we see is that the first location, right, the first 4 bits. So let me put this in 32-bit this TI style, and let's narrow this down so that we see only one word at a time. Okay, so we are seeing one 32-bit word at a time. So that's why the first address is 0, the second address is plus 4. So address is 4, then 8 and C, and so on and so forth. So the first location, that is at memory location 00000, we know that the 32-bit word that is loaded here is the stack pointer. Okay, and so I expect that this value should get loaded into my stack pointer register, which is R13. So we see that has happened, and all the other registers got basically blanked out. Okay, so the system reset. And the second thing that happens is that the immediate next location, that is location 4567. Okay, so the 32-bit word just after the stack pointer address, this is the reset vector. So what is going to happen now is that the system has reset. We have loaded this value into R13. We have loaded this value into PC, program counter. And by the way, why is it not 309? That's because the least significant bit is always going to indicate that we are going to go into thumb mode, right? So the 1 in the least significant bit, that is the 0th bit, tells us that we are going to thumb mode, and the address part, we ignore that 1 bit, and so the address is 308. Another thing to watch out for is the fact that this PC is never going to have 1 in the last 2 places, right? Because we are always going to execute 32-bit words. So this is 308. So now we see what is at 308. At 308 there is a branch, which means basically a jump. Okay, and where does it jump? It goes to this function called noInit noargs. So let's see what's going on there. Okay, so the moment I'm going to do single step debug, the moment I single step, I should end up at this function called cin int 00 noInit noargs. Okay, so this is the function here. Now what's happening in here? Let's just quickly take a look. So this is this function that has been written, cint 00 template, and it has 2 arguments, 0 0. So what is this 0 0? If we go up here, this is that template. Okay, so 0 0 means 0 for needs arguments and 0 for needs init. Okay, so in this particular case we are calling this function with 2 things. One is that we don't need any arguments, as in this main doesn't need any arguments, and second 0 means that there's no initialization that is needed. Okay, so what is happening inside this? So let's take a look. So first is we are going to set this main stack pointer to this particular value, so this stack end. Then we are going to send we are going to check if our floating point unit needs to be enabled, then we will initialize this FPU. So let's take a look at that one by one. So this is what is happening. So we are initializing our MSP, main stack pointer. So that happened, and then there is some instructions for the FPU, which I think is not happening in this case because we have we really don't need let's see, yeah, so this time we have not even initialized this FP. Oh sorry, FP is yeah, so I guess this time the FP also has not got initialized because none of this has happened. Okay, so we have not assigned these values anywhere, or have we? Maybe we have. I think this is what is happening. So FPU is getting initialized. So here is the FPU, and FPU is getting initialized, and then we are back to our function, and then we are going to simply go to this system pre-init. Okay, so what is happening inside pre-init? Pre-init right now is basically a place where you can put your own code in case you want to do anything before main gets called, right? So we don't want to do that. So then immediately we come back here, and then the next thing that is going to happen is that branch link, we are going to go directly to main. So there we ended up in main. So you may be wondering, okay, after all this discussion, we didn't do any initialization, we haven't really done anything, and that is quite simply because there was nothing to initialize. So if you see, there really weren't any variables that had to be initialized at all. Okay, so let's put some variables and see how they get initialized. Okay, so I have just saved all my edits here. So what I'm going to do is, so there's some modifications here, so I'll just git checkout. Okay, so now I've added some variables. What you see here, I've added one array called array_val, and I've added an uninitialized int array called zeros. Okay, so this is initialized values, uninitialized values, and both of them I have kept outside this main function, so they are global in scope. Okay, so let's see what happens now. So let's do a build again. So build has succeeded. Let's just check. The only warning is that this loop is not reachable, which is fine, and let's go debug. So again, by default, our debugger is going to start up and finish all this code and give us a system that is waiting at main, but we don't want that. So I want to go see what happens before that. So I'm going to do system reset again, right? So we have done system reset again, and now let's take a look at the memory space again. We see that at reset, program counter is set to 49A, and that is this value here, right? This is your reset vector, which is 49B, and you can see that at 49A, the value here is reset ISR. Okay, so that's your reset routine. Then you can see the stack pointer is 20000 So let's go and see where the stack pointer got set. So that, yes, that has gotten set here. And so now next thing that we have to do is to see what happens next. So let's single step, and as expected, we are going to end up inside this C template. And now if you see, we are calling this function. So of course the auto generated part of this code is calling this with argument 1 here. Okay, so if you see, where is the definition of this? This is defined as needs args needs init, right? So needs arguments, of course, 0. Main doesn't require arguments in most sane conditions, in embedded C at least, but this needs init now is 1. Okay, so now let's see whether that is actually happening. So let's step through this. This was, I think, the initial part where your FPU and all got initialized. Then there's a pre-init call, where in case you wanted to do any pre-initializations, of course you can go and do that. And then we come back to this initialization. So by the way, I was doing step over, that is why we missed that call to pre-init. So just if we want to make sure that we see that, so we can do this step into. So this is the FPU being initialized now, no op. Then this is system pre-init, so we got called into this system pre-init. So pre-init will get called before any initialization happens, in case you want to do any low level initialization. So you can go and check this out, right? So pre-init is also called in case you want for the user to insert application specific low level code. So we don't have that, so let's step back into this init here. Now this is our actual initialization function. Okay, so what is happening here? So now basically this is sort of a loop which copies data. That's basically what is going on here. So if you look at this area here, what I want to see is, let's take a look at hang on. Okay, so this is basically the function that does the initialization. So there's basically these data tables which this code is going to copy. So let's just take a look at how it's doing that. So assembly step into, and it's basically checking, you know, if there are some table pointers, and you want to check whether you are within the limits, and then, you know, there's a load address, there's a run address, and then you basically have to do a copy. So let's get into that copy function. So this is our copy function. Okay, and I won't get into how this decompress and all is happening, because I'm pretty sure that this data is not written compressed. It is uncompressed. It is being compressed in some way and then written into memory, because you don't want to really take up too much flash for storing your initialized variables also. So for now, let's just focus on this particular loop. So this I equal to 0, I less than char bit, and that's basically what is happening in terms of decompressing the data. But let's not worry about that. Let's go directly to this line, which is basically being executed over and over again. Okay, so what is happening here is that we are loading a byte from R12 address. Okay, so where is R12? That is this 4B2. Okay, so let's go and see what's going on at 4B2. So hex 4B2. Okay, so 4B2, and now we are interested in seeing our data. So I'm going to put this in 8-bit data format. Okay, and I know where is it going to end up. Okay, so it's going to end up, so LDRB R0 from the location pointed to by R12. So we are going to read in this value, and STRB, we are going to store that byte in the location pointed to by R1. So what is R1 pointing to? R1 is pointing to our RAM. Okay, it's pointing to our stack area. So 200, let's go and take a look here. So 200, 200. So there we go. So you can see that this array val, this has already been allocated for that array that we were talking about. Okay, now because I did a reset, now these values have actually all been already initialized. So basically this part didn't get cleared out. So let me go and, just for sake of showing you that it is actually getting initialized, let's put all of these to 0, which is the case if, you know, we had woken up from power up, right? And let us also put some random values here. Let's say a 5, 9, just something here, so that we know that it gets actually cleared to 0. So let's see what is happening. So the first thing that it does is strb you are going to write a byte out here. So you can see that step, and you can see this first value got written here. Okay, so let's iterate through this loop once again. And now you will see that this write char, no, so you will see that the second value gets written as well. So you saw second value got written. Then, and the simple reason for why it's not just a question of copying values, it's because this is compressed, so it's actually doing the decompression and then writing values in. So you can see that this 3 has come in. Let's run it. Couple more times. Actually, what I can do is I can put a breakpoint here. So you can see that next character 4, the byte value 4 got written, then 5 has gotten written, then 6 got written, and so on. Okay, so basically what we have done is, and now you will see that we are going to break out this of this loop, because we are done basically. So there should be one more, because you'll write a 0 as well, right? Oh, sorry, didn't have any other breakpoints. We ended up breaking out of the loop completely. So let's stop here and restart our debugging session. So basically this is just a quick demo to show you how the values actually got copied, and just an insight into the fact that it's not literally just copying, it's basically doing some decompression, because it doesn't make sense to store all of your contents in memory pretty much as is. So it's doing some amount of compression. Yes. So I hope we have our breakpoint here. So I can run this, and now you will see that yes, indeed, these values are getting written. So you'll see that there are some junk values out here, which I'm not sure how they ended up here, but they should get cleared out as we proceed. Let's see, there we go. So you can see that these values are getting set to their correct values. So this became 0. There were some junk values here, and you can see there's some A5 out here, which I think every iteration that we go through this became 4. Now this has become 5, you see. So all the data that has to be initialized, now it is getting, that got copied in. Okay, so now there we go. So everything got clear out, and you can see that because I of course did run zeros of 5, so that data also has gotten written into got initialized to 0. Okay, so that's just a quick demo of the initialization code that is already present, and how to basically take a look at what it's doing and how it's doing.